Hello students, welcome back to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So today we are going to discuss one of the most important concept, that is optical isomerism. Okay, so please join our WhatsApp channel, link is there in the description section, so you can get access to all the class notes, PDF and mock test and solutions. Okay, now coming to now coming to this one. So today will be the part 4 on which we are going to discuss optical isomerism in detail. Okay, next class will do reaction mechanism, qualitative analysis, quantitative analysis and purification. So these are small topics, will be covering it, but yes, this is very important, optical isomerism. Many of you have many doubts in this, so I want all of you to sit with a notebook and a pen, okay, and do these concepts, revise whatever I am discussing to write these points. Okay, fine. Weightage you can see. Okay, so I want to draw your attention towards the PU2 success blueprint test series. Okay, this is a test series brought to you by Diksha to help you to get 95% or above in your PU2 examination. So this test series contains 12 mock tests, which includes 8 full length papers and 4 part tests. Okay, apart from this, you will be getting the solution videos with detailed explanation, one shot revision videos and doubt clarification classes. Okay, and all this you can avail at a very minimal and discounted price of 599 rupees only. So students, if you are someone who wants to crack the board examinations with 95% and above, please do not delay. Go to the registration link in the description section, click on that and purchase the test series. The first test series is already out on 15th of December and the question paper was really good to help you to prepare for the PU2 examination, right? So the next test will be on 22nd December. So make sure that before this 22nd December you purchase this and get ready for the 22nd December test. Okay, fine. So coming to optical isomerism, what all things we are going to discuss today. First we will discuss about some basics, what is optical isomerism and all, chiral center. Next we will discuss about plane of symmetry and the center of symmetry, and next we will discuss about polarimeter experiment, and lastly we will talk about optical activity. Okay, so now coming to the basics. So first see here, what is isomers? So all of we know that isomers is something which has same molecular formula, right, but different structures, right? We have all defined this one as isomers. Next, what is stereoisomers? Stereoisomers, we know that they have same molecular formula and bond connectivity, right? The bond connectivity here is also same. Okay, bond connectivity is also same. What is different in what is different in stereoisomers? Different spatial arrangement. Okay, different arrangement in the space, right? Next we have discussed in optical stereoisomers, geometrical isomers we have completed in the last class. So what is optical isomers now? Optical isomers also have same molecular formula and bond connectivity, right? But what is the speciality? Can rotate plane polarized light. Okay, so optical isomers are those isomers which can rotate the plane polarized light. Now what is plane polarized light? What is this rotation? We will discuss in that. But for now you can understand what are optical isomers. These are those isomers. Suppose I say that A and B are optical isomers. That means A and B can rotate the plane polarized light, okay, in opposite directions. Okay, or you can just understand that A and B can rotate the plane polarized light. Okay, fine. So now coming to something called as chiral center. Okay, what is chiral center? So a chiral center is a carbon containing 4 different groups. Okay, chiral center means a carbon which is having 4 different groups. We know that carbon forms 4 bond, right? So carbon can form 4 bond, and if all these 4 bonds are different, okay, then we can say that that particular compound is chiral. Clear? Okay, now here is an example. I think you can visit, this structure is visible, or let me draw it here. Okay, I have one chlorine here and I have one methyl group here. So you have to check each carbon and tell me whether it is a chiral or not. Now if you check this carbon, okay, it has one side chlorine, one side H, one side CH2 and another side CCH3, right? All the four groups are different, so this is a chiral carbon. Now if I consider this carbon, if you see this has two hydrogen, right? Now all the four groups are not different, so it is not chiral. The same thing is for here also, right? This is not chiral. Next, here also the same thing, it is not chiral, and this one, this is not chiral, right? Now if you consider this one, right, here we have one CH3 group, here we have one H group, okay, and then if you see this side one CH2 group is there and this side one chlorine group is there, right? So this is also different group, so we have two chiral carbons in this particular compound, okay. So now coming to something called as plane of symmetry and center of symmetry. So first let us understand about plane of symmetry. Plane of symmetry, okay, or we can call it as POS. Now see, an imaginary plane of symmetry means what? It is an imaginary plane which divides the compound into two equal halves, okay. If you take a plane or you cut the molecule in two parts through a plane and both the parts are equal with each other, then we call that plane as plane of symmetry. Now why we are studying all these things, I'll tell you, okay. Just for now understand this one. Let us see this particular example, okay. When you do this question, plane of symmetry, imagine this as spheres, okay. So now you see, if you pass a plane like this, okay, pass a plane through this molecule or through this sphere, then can I see that both the side there is hydrogen, right? So can I think that, okay, both the side it is equal? So yes, this molecule has a plane of symmetry, okay. Next one, if you see, what I can do is, if I divide like this, okay, then you see this side OH, this side H, but this side H, this side OH, so it is not what I can say, it is not the plane of symmetry. Or else if I divide in this way, okay, in like this, if you cut like this, then also you see CH3, CH3 is correct, but OH and H is not correct. So that means it has no plane of symmetry. Next one, if you see, you divide this molecule in this way, okay. So you see this side bromine, this side bromine, this side hydrogen, this side hydrogen, right? It is equal, two halves are equal. So yes, that means this has plane of symmetry, okay. Next, here if you see, just divide the molecule in this way, okay. You can see CH3, CH3, H, OH, H, OH. So these are two equal half, right? Both the halves are equal. So that means this has also plane of symmetry, okay. Clear? What is plane of symmetry? It is an imaginary plane which can divide the compound into two equal halves. Now let us go for understanding something called as center of symmetry. Center of symmetry. Okay. Now see, center of symmetry, first of all you need to check where you need to check center of symmetry, or where it is possible. You need to check center of symmetry in only in one place, a 4 or 6 membered ring. Or basically I can say even membered ring, okay. In case of even membered ring, you need to check the center of symmetry, okay. Yes, this is a 4 member carbon, right? So yes, here we can check for center of symmetry, okay. Now you see, if you see from here, okay, what you have to do, you have to check on both the sides. If you find the same group on both the sides, okay, then you can say that it is having a center of symmetry. Now see this structure, I want to draw it again so that it is more clear. It is like this. You have here chlorine, so now you can see here that if I draw this, chlorine is above the plane, okay. One second, yeah. So this is another chlorine molecule here, above the plane, right? We have discussed what is this solid line, and I told you to watch all the videos, otherwise if you miss one video also you won't be able to understand the concepts, right? So that means what? You can imagine that this chlorine, okay, these two chlorine are above the plane, means there is one chlorine here, and I will show you one more here. So it's like this molecule is there, right, and the chlorine is on the two sides, okay, you can see here. So but we need, if center of symmetry is there, that means one chlorine should be above then and another chlorine should be below the plane, okay, it should be like this. Then we can say that if you go front and if you go back you can find the same element, then it is called center of symmetry, right? But if I have two groups like this, right, if I go down, okay, if I go down then I won't find the same chlorine which I found here, right? So that is why this is not a center of symmetry, okay. Next one, if you see here hydrogen is present, right, and I can draw like this, here it is not mentioned, so we can say based on this it has no center of symmetry, okay. Now this is a 5-membered ring, I told you have to check only in 4 and 6, so here also no center of symmetry, okay. Next, coming to this point, okay, so here you have CH3 group, and here you have CH3 group, here you have CH3 group, and here you have CH3 group. Now if you see here the same thing, right, this is also above, this is also above, right? So you, when center of symmetry comes, from the center you need to go front and back, right? So that means here you are going front, but here you should go down the plane, okay. Suppose this is the plane, let me show you again here. See, suppose this is the plane, okay, this square you can see, this is the square, okay, and you have CH3 groups attached on 4 sides. So if one CH3 is attached here and another CH3 is attached like this, one here or above, here also above, then there is no center of symmetry there. If one CH3 is attached here and one CH3 is attached here, okay, below it, that means you have to go front or above the plane and you have to go below the plane, then you will find a CH3 here and a CH3 here, then you can say that it has a center of symmetry, okay. So what I am saying, suppose this is a plane, okay, suppose this is a plane, you have a group here, okay, on this side, and another group should be below here, okay, this side, another group should be here, then that this group and this group are having opposite to each other, right? So now if I show that, so this is no center of symmetry, but here you see this one is going up and this one is going down. So yes, this has, yes, there is a center of symmetry, okay. If you see here, same, I have CH3, I have CH3, I have CH3, and I have CH3. So now you can see here you go down, here you go up, CH3 found, same thing here, right? So yes, it also has center of symmetry, okay. So the point here is, in a molecule there can be more than one plane of symmetry, okay. So what I can say, we can have more than one plane of symmetry is possible, okay. But in case of center of symmetry, it is always one center of symmetry, okay, clear, fine. Now coming to this, something called as polarimeter experiment. So I told you in the starting that a compound is optically active if it can rotate the plane polarized light, okay. Let us understand that one. So here a light is there, okay, you can see this light is having fields in all direction, okay, it has field in this direction, and this direction. Now when you pass this light through a polarizer, okay, you can find only one type of light, or there is the linearly polarized light, the light is having only one field, okay. Now there is this sample cell containing molecules, okay, so you have your molecules in this sample. Now after the light which is having this only one polarization, this light is called as a plane polarized light, okay. So now when this light passed through this sample, you see it is rotated here, optical rotation due to the molecules. The light has rotated. So this ability of the molecules to rotate the plane polarized light is called as optical activity, okay. So all molecules cannot do that. There are certain conditions with which you can say that whether a molecule is optically active or not. So if a molecule can rotate the plane polarized light, then that molecule is called as optically active, okay, optical active. Now if suppose a compound is given A and B, we cannot say whether a molecule is optically active or not by just seeing it. Okay, the only way possible here is you have to put it in this experiment, you have to put it in this sample, you have to pass the plane polarized light through it, then you have to check the rotation. If the rotation is there, then only you can say that it has a plane polarized light. Okay, so that is why very important that you should, like, you cannot by just seeing the molecule you cannot say it, you have to do this experiment. Okay, now suppose we are sitting in the exam, okay, and we have got this question, two molecules are given to you, A and B, and it is told that find out which is optically active. Then what we need to do? We have to go to the lab and then we have to check the sample and then we will tell whether it is optically active or not, right? That is not possible. So because of this, you know, the scientist people, they are very brilliant. So they have given some conditions, okay? On the basis of that condition, without even going to this plane polarized experiment, we can say that whether the compound is optically active or not. Okay, so first of all, the first point, what you mean by optical activity? The optical activity meaning is any molecule, if it has the power, if it has the ability, if it has that capacity to rotate a plane polarized light, then it is called optically active. Now whether a sample or whether a molecule will rotate or not, that we can know only by doing this experiment. Okay, but every time it is not possible. The scientists, to make our life much more like they want to make our life simple, so what they did, they give some conditions based on which we can say that whether it is optically active or not. Okay, so let us see those conditions. So first of all, what do you mean by optical activity? It is something which can rotate the plane polarized light, okay, which can rotate the plane polarized light. Now the rotation can be in two ways. It can be either anti-clockwise, right? If it is anti-clockwise, then we will call it levorotatory. That compound is called as levorotatory if it rotates in the anti-clockwise. And if it rotates clockwise, okay, if it rotates clockwise, then we will call it dextrorotatory. Okay, fine. Now let us understand the conditions for optical activity. What are the conditions? So if a molecule has plane of symmetry or center of symmetry or both, then it is always optically inactive. So if a molecule has plane of symmetry and center of symmetry, it is optically inactive. That means it will not rotate the plane polarized light. If the molecule has plane of symmetry but no center of symmetry, then also it is optically inactive. If the molecule has center of symmetry but no plane of symmetry, then also it is optically inactive, means it won't rotate the plane polarized light. And if the molecule has neither plane of symmetry nor center of symmetry, then it is optically active. Okay, so what is the condition for optical activity? It should not have any plane of symmetry or center of symmetry. Okay, now coming to conditions, we will explain in detail. So now see, if in a compound there is only one carbon and that one carbon is chiral carbon. Chiral carbon, we have discussed what is there. It has 4 different groups. Okay, so if one chiral carbon is present which has 4 different groups, then we can say that optical active. Okay, then it will be optically active. Okay, always, you do not have to think about whether plane of symmetry, center of symmetry, nothing. If only one carbon is there and it is chiral, chiral means it has 4 different groups, then definitely that compound will be optically active. Optically active means that compound can rotate the plane polarized light. Okay, now if you see, if in a compound more than one chiral carbon is present, then there is something to be thought of. If there is more than one chiral carbon is present, then and the molecule is acyclic, means it is a open chain structure, okay, linear structure. Okay, in that case you have to check for plane of symmetry. If plane of symmetry is not there, then it is optically active. If plane of symmetry is there, then it is optically inactive. Next, if it is a cyclic ring with odd number of carbons, okay, cyclic ring with odd number of carbons, then also you need to check only plane of symmetry. Okay. Next, if it is a cyclic ring with even number of carbons, means either 4 carbon or 6 carbon, in that case you need to check both center of symmetry and plane of symmetry. Okay, center of symmetry if it is there, then also optically inactive. Plane of symmetry if it is there, then also optically inactive. Both plane of symmetry and center of symmetry should be absent. Okay, so there are 3 cases. One is open chain. If there is an open chain, you need to check about the plane of symmetry. If it is a ring structure or with odd carbon, then also plane of symmetry. if ring structure with even number of carbon 4 or 6, then both center of symmetry and plane of symmetry you have to check. Okay, clear. Now we will do some practice questions. Okay, the first question: if a compound has just one asymmetric carbon, asymmetric carbon means what? Asymmetric carbon means chiral carbon. Okay, if a compound has just one asymmetric carbon atom, it is always chiral, right? Chiral means again it is always optically active. Right, this statement is correct. Asymmetric carbon is having 4 different groups, that means it is chiral, it is optically active. If a compound has more than one asymmetric carbon atom, it may or may not be chiral, right? Yes, that is also correct, because it depends whether it has POS and COS, right? So both statement 1 and 2 are correct. Option number 1 is, so C is the correct answer. Okay, next, which one of the following is a chiral molecule? Okay, chiral molecule means you need to think, it is asking which of the following compound is optically active. Okay, that is the question. Let us draw the first question. 1,1-dibromo 1-chloropropane. Okay, so you have propane means 3 carbons, and you have bromine, bromine and chlorine, right? So you can see on the first carbon 1,1-dibromo 1-chloropropane. This is option number A given to you. Do you find any chiral carbon here? No. This carbon has 3 hydrogen, this carbon has 2 hydrogen, and this carbon has 2 bromine, right? So there is not even a single carbon which has 4 different groups. So that is why this option is incorrect. Next, 1,3-dibromo 1-chloropropane. Okay, let us see. You have propane again, 1,3-dibromo. So here we have bromine and here we have bromine. Okay, and other 2 are hydrogen. Okay, 1,3-dibromo and 1-chloro. So again it is 1-chloro. So this one is chloro. 1 second. Yes. Okay. So if I see this carbon, it has 2 hydrogen, this carbon has 2 hydrogen, this carbon has one side methyl means carbon, one side bromine, chlorine and hydrogen. This carbon is having only one asymmetric carbon. Okay, it has only one asymmetric carbon, and we have studied that if it is having one asymmetric carbon, any compound, it is always optically active. So yes, I can say that this compound will be optically active. Next question, let us see 1,1-dibromo 3-chloropropane. Okay, let us see option number C. You have bromine, bromine and hydrogen. 1,1-dibromo and you have hydrogen, hydrogen here. So you can see 1,1-dibromo and 3-chloropropane, right? Okay, so now you can see this carbon is having 2 bromine groups, this carbon is having 2 hydrogen and this carbon is having 2 hydrogen. So there is not even a single carbon where all the 4 groups are different, so it is also optically inactive. Now let us see the option number D. It is 1,3-dibromo 2-chloropropane. Okay, so you have here 1,3-dibromo, here bromine group and here bromine group, here we have H, here we have H, here we have H, here we have H. 1,3-dibromo 2-chloropropane. Okay, now if you see this carbon, this side chlorine, this side H, right, and this group is same and this group is also same, right? So this carbon is not having all the 4 groups different, this carbon is having 2 hydrogen, this carbon is also having 2 hydrogen, right? So since there is no single carbon where all the 4 groups are different, so this is also achiral, or we can say optically inactive. Okay, now let us see the next question. Which of the following compound is a chiral compound? The same type of question again, 1-chlorobutane. So if I see option number A, 1-chlorobutane, so this is butane and you have chlorine. Here we have 2 hydrogen, okay, here 2 hydrogen, 2 hydrogen, here we have 3 hydrogens, right? So can we find any one carbon here? Can we find any one carbon which has all the 4 groups different? No, right? So that is why this is optically inactive. Next, 2-chlorobutane. So if I draw 2-chlorobutane, okay, now here you see, yes, now you see this carbon this carbon is having 3 hydrogen, this carbon is having 2 hydrogen, this carbon is having 3 hydrogen. But if you check this particular carbon, it is having 1 chlorine, 1 hydrogen, one side methyl and one side ethyl group. These two groups are not same, right? So this is having 1 chiral carbon, and if there is only 1 chiral carbon, then it is definitely optically active. Next, option number C, if I see, what is it? 1 chloro, 2 methyl propane. Okay, so we have propane, 1 chloro, 2 methyl, okay, and propane. Yes. Now if I see this particular carbon, it has 2 hydrogens, right? This carbon has 1 hydrogen, right? Now if you see this carbon, here we have a chloromethyl group, here we have methyl group, and here also methyl group. So 2 groups of this carbon are same. Next, if you check this carbon, it has 3 hydrogens, so this is also not optically inactive, this is optically active, so that is why that answer is wrong. Next, you have 2 chloro, 2 methyl propane, 2 chloro, 2 methyl. Okay, so now if you see, this is propane, right? This carbon is having 3 hydrogen, this carbon is having 3 hydrogen. Now this carbon is having 1 chlorine and 3 methyl groups, right? Same groups are present, so this is also optically inactive. Okay. Next, question number 4, which of the following is optically active? Okay, so options I have drawn here. You have to find optically active, means there should be 1 chiral carbon at least. Here, can you see any chiral carbon? No. Here 3 hydrogen, here 2 hydrogen, here again 3 hydrogen. So that is why this is not the answer. Here if I see, okay, this carbon, if I see, there are 2 hydrogens on this one, not a different group. Here if I see 2 hydrogen, here also 3 hydrogen. But if I see this carbon, it has 1 CH2OH group, 1 CH2CH3 group, and 1 OH and 1 H group, right? So yes, this has all the 4 different groups, so that this can be the answer. Next, if I see this one, okay, next question, if I see this particular structure, you have CH3 here, OH here, CH2, CH3 here, H here, and I see this carbon is also chiral carbon, right? So that means I can say that this group is also optically active. Okay. Next, you have to tell here you can see 2 chlorine and 2 fluorine, right? So these are not different groups, so this is not there. So which is optically active? B and C. Okay. Fine. Next, which of the following is again optically active? So now if you see here, okay, this carbon is having 4 different groups. This carbon is having also 4 different groups. Now when you have more than 1 chiral carbon or 2 chiral carbons, you should check for plane of symmetry and center of symmetry. And remember, center of symmetry you should not see in the open chain structure, right? Only plane of symmetry. So I can see that a plane of symmetry exists here, right? If I write ET in the form of this ET, I can write like this, CH2 CH3, right? Then you can see the same half is present on both the side. There is a plane of symmetry, that means optically inactive. Right? Next, coming to this one. Here you see this carbon is optically, carbon is chiral because 4 different groups. This carbon is also chiral. But here you can see a plane of symmetry. So we have a plane of symmetry. So it is optically inactive. Next, option number C, if you see this carbon is chiral, this carbon is also chiral, right? But you can see there is no plane of symmetry here, right? There is no plane of symmetry because you see if I draw a plane here, here it is OH and here it is CH3. So yes, this has no plane of symmetry, that means it is optically active. Okay, option number C. Next, if you see here, this carbon is having only 1 group, so you can see here we have ethyl group and here also ethyl group. Both the groups are same, so it is achiral, so no optically inactive. So I can just write down optically inactive. Okay. Next, which of the following is optically active? Again, so here you see, when you see a cyclic member, 4-membered or 6-membered, you have to check both POS and COS, right? So now in this compound you can, oh sorry, one second. Okay, now if you see in this particular compound, okay, if I draw a plane of symmetry like this group and this group are equal, right? That means it is in the plane you have one side, one group, and the same, like I'll draw here. I want to show you, I can show here like this, 2 groups, okay? 2 groups are present on the, like, so if you cut it you will get the same half on, like same group on both the sides, right? So that is why we can say that here we have, there is a plane of symmetry. If plane of symmetry, then no optical activity. Here if you see, yes, if you cut the molecule in this way, okay, divide it in this way, then this group and this group are like mirror images of each other. So yes, this also has a plane of symmetry. Okay, now what about center of symmetry? Here no center of symmetry. Okay, here also no center of symmetry. Okay, next if I see here, you can cut the molecule in this part. Okay, if you cut the molecule like this one and this one will be exactly half of each other. So yes, this has plane of symmetry. Okay, and it also has center of symmetry. You can see, you can go here and you can go down, you will find the same group, and it has also center of symmetry. So this is also not optically active. Now here if you see, this molecule do not have any plane of symmetry because this group is below the plane and this group is above the plane, right? No plane of symmetry and no center of symmetry as well, right? If this group had been here, then we will get a center of symmetry, but here there is no center of symmetry. So that is why this is optically active, and answer will be option number D. Okay, so yes students, that's all regarding optical isomerism. So this is the basics. If you understand this much, then your KCET exam will be done definitely. Okay, you do not need more from here. We'll do in the next class the reaction mechanisms and all. And now I want to again tell you about the test series. So I have already discussed in detail. So if you want to buy this test series, the link is there in the description section. Please go there and click on the registration link, purchase the test series at a very discounted price of $599 only. Okay, that's all students in this class, and see you soon in the next class. As I told you, please do not miss these classes. These are very important to understand the basics, to master that fundamentals of organic chemistry, right? If you do these 7 lectures daily, half an hour to 40 minutes, then your organic chemistry will be solid. Okay, so that's all students, and see you soon in the next class. Thank you, and please do not forget to subscribe the channel if you like this content.